Hi everyone. So in this video I'm going to talk about MAPE, which is mean absolute percentage error. It's essentially a way to measure the accuracy of models that you are carrying out, any kind of modeling. So this could be marketing mix models, this could be predictive or forecasting related models, be it any kind of model you are trying to understand the error terms and from there just how accurate the model is. Now MAPE is just one of the metrics. There are many others like RMSE or MAE. Now the question really is, how good are these error terms? I'm not going to obviously talk about all the error terms, as you understand from the title of the video. This is only going to be about MAPE, which is a specific error term, and we're going to actually look at how this error term can be misleading. So you'll see that I'm looking at a certain Google Colab notebook, and this Google Colab notebook is basically giving an example, and it's called, as you can see, infinity synthetic example, because I'm going to show how MAPE can actually turn out to be infinite even if the model is relatively decent. And I'm going to show you how the code has how the code works and how the data has been generated, because it's actually important to understand the data set. And the whole point of this video is actually going to be about that. Like, it's not necessarily only about the model, but it's also going to be about the data set as to how your error terms look like and whether or not they're giving you the right direction, which is your ultimate objective, right? Your error terms should give you directionally a good understanding of whether or not the models are accurate, or going to or are they going to, if they're going to help you take better decisions. So the code here obviously starts with loading some common libraries and packages. Regression related R squared is another sort of accuracy measure of a regression model. And NumPy and pandas are obviously most important. Then you have, for reproducibility, very common, you obviously pass 42 to random dot seed. And then you have the date ranges, and this is the random data generation process. The way the data has been generated is that there is a strong correlation between so as you can see here, between the different values. So meta spend and Google spend, meta spend and Google spend are connected with a random value, as you can see. They are sort of associated. You also have the TikTok values for spends and YouTube values for spends. So that's how this has been generated. And the reason why Google and Meta, by the way, this is basically the result of an LLM prompt, and the way I prompted it was by saying that Google and Meta will be the most closely associated, in the sense that they should be the ones who will be mostly responsible for the outcome variable. And the outcome variable is obviously going to be sales, as you can see here. So there are some organic impressions as well that have been generated. And then there is also the organic search impressions. And then you finally have the sales. So as you can see, the sales are given as a sort of a linear combination, with certain coefficients which are sort of decreasing, as you can see, as we move from Google spend towards the organic. Anyway, so that's your data generation process. There's also a final term here, as you can see, this np random dot normal, this part here, that gives you an error term. Okay, so the data frame is the final table that gets built, and so within that we have the different columns like date, Google ad spend, and the different ad spends, the impressions as well, and finally the sales, which is our target variable. So this is our file, and this is the final table as it appears. And if I just show you this table here, so we have all these columns, and you'll see the different values corresponding to each of these dates. So as you will see, the date actually ranges, I think, from so it is 90 days starting from the 1st of January 2024. So that's how the data has been generated. If you want an idea of the data set, this is how it looks like. So the different columns here, you'll also see, interestingly, the min and max values for each of these, and the spread, basically. If you want, you can look at look at the values here. So the mean value is very similar for Google and Meta ad spends. For TikTok and YouTube, also kind of similar. For TikTok, it's a little lesser. Impressions values are closely aligned. TikTok is again a bit lesser, in line with what we saw with spends. There's also some decent Google search impressions, organic search impressions as well. Now actually look at the minimum values as well, and you'll interestingly see that there are no non-zero values for any of these input values. For sales though, interestingly, you'll see that there's 0.00, or that's basically zero, so that's the minimum value. That is actually the most important point, as we'll find out in just a moment, because you don't really want to you essentially don't want values which are non you want values which are non-zero. You don't want zeros, or you don't want missing values in your data set. So that's basically part of what's called an EDA. That's the data cleaning process. So in terms of standard deviation, there's reasonable standard deviation, as you can see, for most of these values here, and for impressions also. So yeah, we can actually check out the standard deviation as a percentage of the mean value, and that's always a good idea. Anyway, so now we are actually going to check whether or not there's a zero value, and this is the a piece of code that actually shows us on which date the sale was actually zero. And we can see that it's on row 42. We obviously saw only the first 5 rows here. So as you know that there are 90 rows, right? This is a 90-day data set. So on the 42nd row is the is 12th of February, and that is where you actually have because it started from 1st of January, so naturally that's the 42nd day in the year. That's when the sales was zero. So that's what this was showing here, the total sales being the minimum value being zero. The reason why I'm walking you through, by the way, through this Python code, is because you should start working a little bit with Python if you're in marketing. I think this will make your life much easier. It's not very hard to learn. If you have questions, you can let me know in the comments. But yeah, this is just a very simple example. Now what we're doing is we're going to try and plot it, and we're going to try and also look at the kind of metrics that we're getting. So what we are looking at is two things happening within this piece of code. First of all, we're doing a linear regression because we want to also find out the error terms and the explainability, which is given by R squared. So we'll have R squared, and we'll have MAPE, and uh, I think we'll have wMAPE as well. Yeah, so that's weighted MAPE essentially. So MAPE is, as I said, mean absolute percentage error. Will give you the definition from the code itself. I probably don't have the mathematical formula written here, but I'll just walk you through it. So the linear regression, this is how you fit a linear regression model. Very simple. First of all, you create x and y, so split between the input variables and the target variable or the output variable, and then you have the R squared. And the R squared is essentially a built-in method, as you can see. So R squared is basically working as a sort of a relationship between y and y predicted. And you can see then there's MAPE, which is given by the difference between the predicted and the actuals divided by the actual values. So that's the definition of MAPE really, and that is expressed as a percentage. And it's very important to note that this is an absolute value. So absolute means that the sign is not important. So whether or not the actual or the predicted is more is immaterial. It's only the absolute value of the difference divided by the actual value. So the actual value is always in the denominator, and that's important. So if the actual value, and by the actual value means what's there in the data set. So as we saw that in the 42nd row, the actual value is zero, right? So you can already see the problem here. So it's going to be divided by zero. Divided by zero means undefined, or it can be split out as infinity. And we'll see in a moment that's exactly what's going to happen. And we also have a correlation matrix that's going to be given as as a sort of a table in this format, as you can see. So from here you'll get an understanding of how the correlation is working. So you'll see that organic search here has the highest correlation with sales. So it's got almost close to 82% correlation, 80.8 correlation, 0.83 I think. Yeah. And in a decreasing order, Meta, Google, spend, and other impressions. In fact, there's a very small negative correlation for some of the organic spends and impressions. Very small negative means that they are very weak correlations. Essentially, don't bother so much about the sign. But you already saw why this is coming out to be the case, because that's how the data set was synthetically generated. But the point here is that this is very, very this is very possible to for it to happen. And the interesting thing is, if I now look at the what I've not sort of got from the code here, I can change that. But or you can do that if you are interested. You can obviously generate other outputs from regression analysis. The typical regression table, you can have far more things like coefficients and all. Here I've only come up with the accuracy measures or the error term. So R squared is 0.7. So 70% of the sales is actually explained by the input variables that are considered here, and you can understand why that's how the data was generated, right? Very very closely aligns with what we have seen. But we have also seen what we are also seeing is that the MAPE is infinite. This is what this entire thing is about. So infinite percentage for a model of, infinite error for a model which has 70% explainability, and we actually saw the data set there is close correlation, right? And we can see from the correlation data as well, that there is reasonable correlation between some of the input variables, not all of course, but some of the variables and total sales. But even then, you will have a MAPE of infinite. In fact, if you drop some of these input variables, in case you are thinking, so let me explain that as well. Let me clarify that as well. So if you're thinking that if some of these less correlated terms, the inclusion of them in the model is somehow causing this, that's not the case at all. So in case you can go ahead and drop some of these ones which are with suppose a very low value or a very low negative value. Go ahead and remove them and just run the model with just a few independent variables, a couple of them which have some sort of positive values, maybe the top three here: Google meta spend and Google search impressions, organic search impressions. Will still get the same result because the R squared will obviously change every time you change the number of variables. There's a chance that R squared might actually drop a little bit because the number of variables will, adding more variables usually increases R squared. But more importantly, and that's why there's, by the way, there's something called adjusted R squared as well, which takes into account if the number of variables is affecting the model or the R squared value in particular. But the MAPE is not going to change because the MAPE depends only on the difference between the absolute and the predicted values, and the predicted values might change, but your absolute value remains still zero for that data point. And because it's essentially a summation, as you can see, if I go back to the formula here, it's a sum. If the MAPE is essentially a mean, right, between the absolute and the um it's a mean between it's a mean of these values, the difference between the y actual and the y predicted. So that's why this is always going to result, and because the actual is in the denominator, it's always going to result in zero, or rather the denominator is going to be zero and it's going to turn out to be infinite. So that's the problem. Like, it's a very plausible model, and you can see now what I've done is I've gone ahead and actually plotted the actuals versus the predicted values of sales. And this is the regular, I'm not going to walk you through the code here, that this is just telling what which axis has what, and the legends and everything. And you'll see that it actually, except for this one major outlier here in sales, when the sales really massively drop between due dates here, uh, otherwise it has very closely followed the pattern, right? Except for this one outlier, which could have easily, by the way, this is actually good practice. If you have such a massive outlier, you keep that in your mind, or you note it down somewhere, and you just remove the outlier and then do the analysis. If you have many such things, then it's not an outlier anymore. But in this case, clearly this is an outlier, right? I mean, nothing comes even remotely close to this value. It's actually good practice to remove this outlier. See, so many things actually comes out of just a small analysis. The only thing we wanted to look at is what actually causes MAPE to be infinite, which is not necessarily a bad model, but an unclean data set. But a lot of other factors also came out, other factors regarding data sets. So this is why it's actually so difficult, and that's why data scientists also say that all the time, that it's so difficult to sort of automate this entire process. Or automation is already there, of course. It's been around for a while, much before even Gen AI came into existence. But it's so hard to see for LLMs to do all of this entirely if the inputs are not refined enough. It can all be done through LLMs, but you really have to understand what you're doing, and that's why it's so important to keep these things in mind. Like, MAPE can be infinite, but if you think that your model is wrong, then you'll be taking wrong decisions as well. You'll probably alter the model and have a worse model. But in this case, you'll continue having MAPE as infinity. By the way, nothing's going to change that. So you may even reject this entire method and try to take some naive approach of decision making, but that will be a bad idea, because here at least you'll get to know the coefficients, you get to know the you know which is causing which is having a greater impact, and stuff. So many things you can do after this as well. This is obviously rudimentary initial level analysis with regression and correlation. Much more things you can do, but the whole point here is that it's a model which where the actuals and the predicted actually closely mimics the values of the actuals. Despite that, you have a MAPE of infinite percentage, which obviously makes literally no sense. It's just because of one single data point which has caused this. So hope this was useful. This is what I wanted to discuss in this particular video. And if you have any questions, do let me know in the comments. Thanks for watching, and see you in the next one.